In 2024, James Webb pointed at the heart of our galaxy, and the image that came back stunned astronomers on Earth. For 100 years, we thought we knew exactly where we lived in the Milky Way. We had the maps, we had the data, we had confidence. Then James Webb pierced through the dust clouds. We are not where we thought. Our distance from the galactic center has been miscalculated. The spiral arm cradling our solar system is far larger than textbooks ever showed. Right now, you are hurtling through the galaxy at 800,000 kilometers per hour, and nobody told you where you're actually headed. By the end, you won't just know your address in this cosmos, you'll finally understand what it means to exist here. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. Every map begins with a vantage point. To map a city, you need to be able to step back from it, stand on a hill, climb a tower, look down from altitude. Distance is what makes shapes visible. Distance is what turns individual streets into a pattern, individual buildings into a grid, individual trees into a forest with edges and a center, and a recognizable shape you can hold in your mind. We have never had that luxury with the Milky Way. We are not looking at our galaxy from the outside, the way we look at the Andromeda galaxy hanging in the autumn sky. That faint smear of pale light we can point to and say, there it is, a spiral galaxy, roughly disc-shaped, seen at a slight angle, 2.5 million light-years away. We know what Andromeda looks like because we can see it whole, the way you see a painting by stepping away from the wall. With the Milky Way, we are not standing on the hill. We are standing deep inside the forest, trying to measure it. Think about what that actually means. Imagine you have been asked to draw an accurate map of an enormous ancient forest. Every trail, every clearing, the full shape of it from edge to edge. But there is a condition. You can only stand in one place, deep inside it, surrounded by trees in every direction. You can see what is immediately around you. The nearby trunks, the patches of sky visible between the branches. You can walk the nearby paths, count the clearings within reach, note where the undergrowth thickens and where it thins. Given enough time, you could produce a remarkably detailed map of your immediate surroundings. It would look careful. It would look thorough. It would look, to anyone, examining it, very nearly complete. But the forest's true extent, where it actually ends, how wide it runs in the directions you cannot walk, the overall shape that only becomes visible from above, would remain permanently out of reach. And here is the part that should unsettle us. Your map would have no blank spaces, no honest gaps, nothing to signal what was missing. It would simply stop at the edge of what you could see and present that edge as if it were the edge of the world. The Milky Way is that forest, and we have always been standing deep inside it, looking outward through layers of stars we cannot rise above, trying to map something whose true shape we have only ever been able to partially see. That is the problem. And for most of human history, we were also measuring it with entirely the wrong kind of light. The Milky Way is a barred spiral galaxy, a vast rotating disk of stars, gas and dust, shaped something like a slow, immense pinwheel seen from above, with a bright central bar of densely packed stars running through its core, and long curved arms trailing outward from that bar in sweeping arcs, each arm a river of stars and gas and stellar nurseries, each one wide enough to hold thousands of solar systems side by side. From edge to edge, the Milky Way spans roughly 100,000 light-years. A light-year is the distance light travels in one full year, and light moves at about 300,000 kilometers, or 186,000 miles per second. Fast enough to circle the entire Earth 7.5 times in a single heartbeat. Even at that extraordinary speed, crossing our galaxy from one edge to the other would take light 100,000 years. 100,000 years ago, our ancestors were still using simple stone tools and had not yet reached the Americas or Australia. The galaxy has been waiting for us the entire time. Our solar system sits approximately 26,000 light-years from the galactic center, roughly positioned between the dense inner regions and the quiet outer disk, in a quieter arm of the galaxy's spiral structure called the Orion Arm. Not in the crowded, turbulent zones near the core, not at the spectacular outer rim. Out here, in what you might think of as the galactic suburbs. To feel what 26,000 light-years actually means, consider this. If you could travel at the speed of light toward the galactic center, the journey would take 26,000 years. 26,000 years ago, the last ice age was still gripping the planet. No city had ever been built. No field had ever been planted. Humans were painting animals on cave walls by firelight, living in small groups, their world unrecognizable from our own. And the center of our own galaxy sits that many years of light-speed travel away from us. Not a distant abstraction, a real distance, anchored to real human time. For generations, astronomers believed they were closing in on a reliable picture. By tracking the movements of millions of stars, by measuring the spread of hydrogen gas across the sky, by comparing the patterns they observed to the structures of other galaxies seen from the outside, they were assembling something, a map, not perfect but reasonable. The broad outline of our galaxy, they thought, was increasingly understood. But here is where the problem runs deeper than anyone fully appreciated. Visible light, the ordinary light our eyes evolved to detect, the light that conventional telescopes were built to capture, does not pass freely through the Milky Way. Between the stars, the vast spaces of the galaxy are not empty. They are threaded with enormous clouds of gas and dust, microscopic particles, each one smaller than a bacterium, drifting in all directions across thousands of light years. And these clouds do something devastating for astronomy. They absorb and scatter visible light the way a thick wall of smoke swallows a searchlight beam. The light enters. The light does not come out. Astronomers call this interstellar extinction, the dimming and blocking of starlight as it passes through the dust-filled spaces between solar systems. And the numbers are genuinely staggering. Through the dusty plane of our galaxy, dust limits what visible light telescopes can see to roughly 16,000 light-years in most directions. 16,000 light-years in a galaxy 100,000 light-years wide. Without the dust, we could see the entire disk. With it, we are looking through a keyhole, reaching barely 1/6 of the distance we would need to see the whole picture. And toward the galactic center, the region we most need to see, where the structure is most complex and most dramatic, the dust is so catastrophically dense that fewer than 1 photon in a trillion makes it through. 1 in a trillion. Imagine 1 billion people each trying to shine a flashlight through a wall of solid stone. Perhaps a single beam from a single person might produce 1 faint flicker on the other side. That is what visible light faces trying to cross the inner galaxy. But there is a second problem, and this one cannot be solved by building a more powerful telescope. We are not observing the Milky Way from outside. We are not positioned above it like cartographers, hovering over a country they can turn and examine freely. We are inside the disk, embedded within it, looking outward in every direction through the very structures we are trying to understand. Every direction we look, we are looking through the galaxy itself, through layers of stars, through drifting dust clouds, through the very spiral arms we are trying to map. Our perspective is not just limited, our perspective is fundamentally distorted by where we stand. Back to our forest. Imagine that on top of everything else, the air between the trees is thick with fog. Not a gentle mist, a dense, uneven fog that thickens dramatically in certain directions and thins in others. You can see perhaps 100 trees in the clearest direction, 40 in another. In some directions, almost nothing. You are mapping what you can see, not what is actually there, and you have no way of knowing from inside the fog which parts of your map are accurate and which are simply the limit of your visibility presented as fact. That is what 4 centuries of Milky Way cartography looked like, and it produced something genuinely remarkable and genuinely incomplete. For decades, the picture that emerged seemed solid enough, a barred spiral galaxy with 4 major arms, our sun sitting in a modest spur called the Orion Arm, radio telescopes which can detect wavelengths that pass more easily through dust than visible light, had traced the broad strokes of the spiral structure. The galactic center was confirmed to host a supermassive black hole, Sagittarius A star, a gravitational colossus with a mass 4 million times greater than our Sun. The general shape of the galaxy seemed, if not perfectly known, at least understood in outline. Then the European Space Agency launched the Gaia Space Observatory. Its mission, to map the precise positions and motions of stars across the Milky Way in greater detail than anything before it. What Gaia returned was extraordinary. Nearly 1.5 billion individual stars, each one pinpointed with astonishing accuracy. If you counted one star per second without stopping day and night, it would take nearly 47 years to finish counting every star in Gaia's catalogue. Gaia measured all of them. Scientists were confident the broad picture was now firmly established. They were not wrong to feel that way. It was the most detailed stellar map ever assembled. It was also, it turned out, far less complete than it appeared, because even with that staggering catalogue, even with decades of radio observations layered underneath it, the inner regions of the galaxy remained stubbornly hidden, not because Gaia had failed, because those regions sit behind walls of dust so thick that even Gaia's instruments could not fully penetrate them. The spiral arm structure near the galactic center was blurry, contested, actively debated among researchers. Key star-forming regions, the vast clouds where new stars are being born right now, at this moment, were effectively invisible. The map had gaps, large ones, and the gaps sat precisely where the most important and dramatic structure lived. Here is what makes that genuinely unsettling. The map did not look incomplete, the gaps had no labels, the blank spaces were not marked as unknown. The map simply ended at the edge of what the dust allowed, and offered that edge as the edge of knowledge. The forest had been mapped to the limit of the fog, and the fog was presented as the horizon. The James Webb Space Telescope was not designed simply to see farther than previous telescopes. It was designed to see differently. Webb operates primarily in the infrared, wavelengths of light that sit just beyond what human eyes can detect. The same family of radiation as the gentle warmth you feel radiating from a fire before you see the flames. Invisible to us, but not to Webb. And infrared light has a property that changes everything for Milky Way research. It passes through interstellar dust clouds that block visible light far more completely than any previous space telescope could manage. In infrared, astronomers can see roughly 6 times further through the dusty galactic plane than they can in visible light. The fog thins, the trees become visible, the shape of the forest begins to emerge. NASA's science team has described the galactic center, hidden to every optical telescope ever built, shrouded behind dust so thick it blocks 1 trillion photons for everyone that escapes, as one of Webb's primary targets. And what Webb has begun revealing there, and in the dense star-forming regions scattered throughout the galaxy's inner disk, is extraordinary. At Sagittarius C, a stellar nursery sitting just 200 light-years from the supermassive black hole at our galaxy's very center, deep inside the region most completely hidden from optical view, Webb revealed star formation so dense, so active, and so unexpectedly complex in its structure that researchers from the University of Colorado Boulder and the University of Virginia described the images as showing an environment no previous telescope had ever honestly been able to study. Thousands of newly forming stars embedded in filaments of gas and plasma, shaped by powerful magnetic fields, emerging from behind dust that had hidden them for the entire history of astronomy. In the W51 region, one of the Milky Way's most intensely active zones of star formation, a team from the University of Florida, led by astronomer Adam Ginsberg, used Webb to look directly through the thick natal dust surrounding newborn massive stars. Stars still cocooned in the gas clouds from which they emerged, still gathering mass, still in the first 1,000,000 years of their existence. 1,000,000 years sounds long. But our sun has been burning for 4.5 billion years. These stars are newborns by any cosmic measure, and they had been completely invisible to every telescope that came before. Ginzburg put it plainly. With previous instruments, the dust was an impenetrable wall. With Webb, now, for the first time, we can see through it. And what these early observations are already suggesting reaches far beyond individual stellar nurseries. The spiral arms may be more active than the old maps showed, the inner regions more dynamically complex, the connections between structures more intricate, more layered, more alive than any previous model described. Webb is not filling in the remaining details of a map we mostly understood. Webb is revealing that parts of the map itself were drawn incorrectly, or simply left blank because the dust made honesty impossible. We are beginning, for what may be the first time in all of human history, to climb above the fog, to see the shape of the forest from something approaching height. And what that view is beginning to show us raises a question that goes far beyond the shape of spiral arms or the activity of stellar nurseries. Because if the map was incomplete, if the galaxy we thought we understood was in fact far larger, more complex and more dynamically alive than the old picture allowed, then what does that mean for our understanding of where, precisely, we sit within it? Our cosmic address, it turns out, is not a settled fact. Pinning it down with real precision has required decades of extraordinary work, and what that work has uncovered about our specific location. Why here? Why this particular region among hundreds of billions of stars, and what that placement quietly tells us about the conditions that made complex life possible, turns out to be one of the most consequential questions in all of modern astronomy. We know roughly where we are, but the closer scientists look, the more they realize that roughly is no longer good enough. And the reason it is not good enough matters deeply, not just for the map, but for us. Our address in the universe is more specific than most people realize. We know the galaxy, we know which arm of it, we know roughly how far we sit from its center. But for a long time, the detailed picture of our immediate cosmic neighborhood was quietly, significantly wrong, and no one had noticed. An address is only useful when you understand what it actually means. Knowing you live in a particular city tells you something, but it doesn't tell you which neighborhood, which street, what lies immediately around you. Whether you're near a park or a highway, in a dense and active district or a quiet and unusual one, surrounded by constant activity or sitting, perhaps unknowingly inside something strange, our cosmic address works exactly the same way. We know the galaxy, but the galaxy is only the broadest answer, the country, not the street. The real questions are far more specific. Which arm of the galaxy? How far from the center? What surrounds us in our immediate region? What kind of neighborhood have we always lived in without ever being able to step far enough back to honestly see it? Those questions have taken decades of extraordinary effort to begin answering, and what the answers reveal is far more surprising than anyone had anticipated. Our sun sits in a structure called the Orion Arm, also known as the Orion Cygnus Arm, or the Local Arm, a curved ribbon of gas, dust and stars tracing one of the spiral features of the Milky Way's disk. Not one of the galaxy's two major arms, a smaller distinct structure running between them, containing our solar system along with a rich collection of stellar nurseries, hot young stars, and familiar constellations. The Orion Arm is roughly 3,500 light-years wide. To feel that scale, if you shrank the entire Milky Way down to the width of a basketball court, about 15 meters or 50 feet, our arm would be roughly half a meter across. A single stride. In that model, you could step across the width of our entire galactic neighborhood in one pace, and the galaxy would still stretch 25 strides in either direction before reaching its far edge. In length, the arm extends somewhere between 10,000 and 20,000 light-years. Estimates have grown substantially with better data. Our solar system sits near the inner rim of this arm, roughly halfway along its length. Not at the turbulent edge nearest the galactic core, not at the sparse outer fringe. Settled, relatively comfortably between two larger and denser spiral structures, the Carina-Sagittarius arm curving inward toward the galactic center and the Perseus arm sweeping outward away from it. From this specific location, the center of the Milky Way sits approximately 26,000 to 27,000 light-years away, a distance so vast that even at the speed of light, 300,000 kilometers or 186,000 miles per second, the journey would take 26,000 years. 26,000 years ago, the last ice age still gripped the planet. No permanent settlement existed anywhere on Earth. The first cave paintings at Lascaux were still thousands of years in the future. The galactic center is separated from us not merely by distance, but by an expanse of time longer than all of human civilization, multiplied many times over. Assembling a picture of this neighborhood required a kind of patient, indirect detective work that has no real parallel in ordinary experience. For most of astronomical history, astronomers used radio telescopes, instruments that detect wavelengths of energy far longer than visible light, to trace the great clouds of hydrogen gas scattered across the galaxy. Radio waves pass through dust more easily than visible light does, which meant radio astronomy could reach places optical telescopes could not. The major arms were mapped, the galactic bar was confirmed, our position within the Orion arm was identified and roughly plotted, but the precision was always limited. Radio maps gave shapes, not exact positions. The picture was broad, impressionistic, the outline of a coastline, not the detail of a harbour. Then the European Space Agency launched Gaia. Gaia was a spacecraft built to do one thing with extraordinary precision: measure the exact positions, distances, and motions of individual stars across the Milky Way. Not thousands of stars or millions, nearly 2 billion. Gaia carried the largest digital camera ever sent into space, containing nearly 1 billion individual pixels. By comparison, a typical smartphone camera carries around 12 million pixels. Gaia's camera was roughly 100 times larger than what sits in the phone in your pocket, and it needed that scale because the measurements it was making were almost impossibly delicate, tracking the motion of stars across the sky with a precision equivalent to detecting the width of a human hair viewed from across a continent. Launched in December 2013 and operating until January 2025, Gaia made more than 3 trillion individual measurements during its 11-year mission. 3 trillion. If you counted one measurement per second continuously, without rest, you would still be counting 95,000 years from now. Modern human beings have existed for roughly 300,000 years. Gaia's data would take nearly a third of our entire species' existence to count. Scientists are still processing it. For decades, the Orion arm was treated as a minor structure, a spur, a secondary feature between two genuinely significant spiral arms. Smaller, less dense, less consequential. The academic literature described it as a local spur, a fragment between the Sagittarius and Perseus arms, not a feature in its own right. Charted, labelled, considered, settled. But the reality was more complex. When astronomers used high-precision radio measurements to pin down the exact distances and motions of star-forming regions scattered throughout our arm, mapping them one by one with extraordinary accuracy, the Orion arm started to look very different from what the old picture described. Its total length was significantly larger than previously estimated. Its rate of star formation, the pace at which new stars were being born along its length, was comparable to the galaxy's major arms, not merely a quiet secondary feature. Its curvature through the galaxy matched what would be expected of a full spiral arm, not a minor spur between two others. Researchers who examined the accumulated evidence concluded that the Orion arm is reasonably considered a fifth structural feature of the Milky Way, not a footnote, but something approaching a principal character. We had been living inside a structure we significantly underestimated for the entire history of astronomy. And no one had noticed because you cannot see the true shape of something when you are standing inside it with limited tools. But the greater surprise was still arriving. and it came from a direction no one had expected. For 150 years, astronomers believed that the stellar nurseries nearest to our Sun, the clouds of gas and dust where new stars are actively being born, were arranged in a roughly circular ring. A 19th century astronomer named Benjamin Gould had first described this arc of star-forming regions in 1879, and the structure had carried his name ever since. Gould's Belt. 150 years of observations, mapped, described in textbooks, accepted as part of the local picture, settled. In 2020, a team at Harvard University, astronomers Alyssa Goodman, Catherine Zucker and João Alves, were using Gaia's precision distance measurements to build a new three-dimensional map of the stellar nurseries in our galactic neighborhood. They were looking for sharper positions, better distances, a cleaner picture of the local structure. They were not looking for anything unexpected. And then the map resolved, and everything changed. What the data revealed in 3 dimensions was not a ring. The ring had never existed, not in space, only in projection, in the flat 2-dimensional view from Earth that had tricked astronomers for a century and a half. What Gaia's precision actually showed was a single, continuous, undulating filament of gas, a wave-shaped structure approximately 9,000 light-years long and 400 light-years wide, cresting 500 light-years above and below the flat plane of the galactic disk. Stellar nurseries strung along it like lights along a slowly oscillating wire. The team named it the Radcliffe Wave. No astronomer expected that we live next to a giant wave-like collection of gas, Goodman said. The language is precise, not unexpected in its details, not slightly off from the model, completely unanticipated. A structure that had been sitting in our galactic backyard for the entire history of astronomy, hidden in plain sight, invisible because the tools to see it in 3 dimensions had not yet existed. When Zucker reflected on the discovery, she put it simply, "It's been right in front of our eyes all the time, but we couldn't see it until now." The Sun sits just 500 light-years from the Radcliffe Wave at its closest point. 500 light-years, meaning the light we observe leaving its nearest stellar nurseries tonight departed around the time of the early Renaissance. Copernicus was a child. Da Vinci was just beginning his career, and the largest known coherent gas structure in our galaxy was already there, completely unmapped, half a millennium's worth of light travel time from our window. What makes the Radcliffe Wave stranger still, it does not just look like a wave. In 2024, a team led by Harvard's Ralph Konietzka published new findings in Nature confirming that the structure physically moves like one, oscillating through the galaxy the way a wave moves through a sports stadium crowd, pulled back toward the galactic plane by gravity, rising and falling in a traveling rhythm that spans thousands of light-years. What causes this motion remains genuinely unknown. Theories range from clusters of ancient supernova explosions to the gravitational disturbance of a smaller galaxy that collided with the Milky Way long ago. The question is open, the tension remains, and then there is the immediate question, not which arm, not which wave, but the space itself surrounding our solar system right now as you sit wherever you are. Our Sun does not sit in an average patch of the Orion Arm. We sit inside a cavity, a vast, roughly spherical region about 1,000 light-years across, where the interstellar medium, the diffuse gas and dust that fills the space between stars, is roughly 10 times less dense than the Milky Way average. Astronomers call this region the local bubble, or sometimes the local cavity, and understanding how it came to exist reveals something extraordinary about the violent history of our immediate neighborhood. 14 million years ago, a cluster of massive stars near this region of the Orion Arm reached the ends of their lives and exploded, perhaps 15 supernovae or more, detonating over millions of years in a sequence of events that would each, individually, briefly outshine an entire galaxy. The combined shockwaves from those explosions swept the surrounding interstellar gas outward, piling it into a compressed shell and leaving behind this vast, heated, emptied interior. You are inside that interior right now. As you read these words, the solar system sits near the center of a cavity blown open by stellar explosions that happened before our most distant ancestors existed. The space surrounding us for approximately 1,000 light-years in every direction is an ancient, invisible room, its walls made of compressed gas, its ceiling of compressed dust, all of it the remains of a catastrophe that unfolded over geological time. And here is the remarkable detail. Our solar system was not born here. We formed 4.5 billion years ago, somewhere else entirely in the galaxy's disk, and have been slowly orbiting the galactic center ever since. We entered the local bubble only about 5 million years ago. 5 million years ago, the earliest upright walking hominins, our distant ancestors in the Australopithecus lineage, were taking their first tentative steps across the African savanna, a world completely unrecognizable from our own, and the solar system they walked beneath had just crossed the boundary into an ancient emptied explosion zone, entering the cavity we still inhabit today. What makes this stranger still, the compressed shell at the edge of the local bubble, that wall of swept-up gas at its outer boundary, is the site of all nearby star formation. Every young star being born within about 500 light-years of us is forming there, in the dense material driven outward by those ancient explosions. Our nearest stellar nurseries, the birthplaces of the stars forming closest to us right now, are, in the most literal sense, built from the ruins of the supernovae that created our immediate home. What Gaia built with positions and stellar motions, Webb is now extending with light. Webb's infrared instruments reveal the precise structures, temperatures, and internal compositions of objects that Gaia could only locate. In the stellar nurseries of the Orion Arm, in the places where new stars are being born right now, some of them within our own local bubble's shell, Webb is imaging what previous telescopes could only suggest. The pillars of creation, the towering star-forming columns in the Eagle Nebula that Hubble had photographed before, were re-imaged by Webb in infrared. The result revealed more than 5,000 infant stars actively forming inside those dust columns. Stars that had been entirely invisible to every optical telescope because the dust columns hid them. More than 5,000 new stars in a single image in our own galactic neighborhood. The data embedded in those images is not just visually extraordinary. It is telling scientists in new detail how stars form in the Orion Arm, how the process unfolds, how long it takes, what structures emerge, and what role our specific location in the galaxy plays in all of it. Webb is beginning to answer the question of why our neighborhood looks the way it does, from the inside, with the precision that only infrared vision through the dust can provide. And what those answers are pointing toward, about the deeper structure of the galaxy beyond our immediate neighborhood, about the inner regions still largely hidden, about the forces that shape everything we live within, is the next layer of the story. Because our neighborhood, extraordinary as it is only the beginning of what Webb has begun to uncover. The neighborhood is more dynamic, more layered, and more surprising than any earlier map communicated. A bubble carved by ancient explosions, an oscillating wave of stellar nurseries that hid behind a century and a half of incomplete data. An arm of the galaxy quietly more significant than its old classification suggested. All of it here, all of it always here, invisible not because it was distant, but because the tools to see it simply hadn't existed yet. But seeing the neighborhood is still only the beginning. The Milky Way's true hidden architecture, the dense inner structures, the star-forming regions packed against the galactic center, the full complexity of the spiral system that contains all of this, remains a deeper question. And it is precisely in those hidden inner regions, the areas behind the thickest walls of dust, that Webb is, producing the most startling images of all. What the telescope has found there is forcing astronomers to rethink not just the local picture, but the full structure of the galaxy we call home. Everything changes near the center, the relative quiet of our galactic neighborhood, the gently emptied local bubble, the slowly oscillating stellar nurseries, belongs to the outer suburbs. Move toward the core, and the Milky Way becomes something else entirely, something far more violent and far more strange, and until very recently, completely invisible. Our neighborhood in this galaxy is, by any honest measure, a quiet place. The stars around us are spread generously apart. The nearest one to our Sun, Proxima Centauri, sits 4¼ light years away. 4 light years of mostly empty space between neighbors. The gas between those neighbors is thin, tenuous, below the density you would find in the best laboratory vacuum on Earth. The local bubble, with its sparse interior carved by ancient explosions, surrounds us with an unusual emptiness. Our arm of the galaxy curves slowly. Our stellar nurseries rise and fall in a wave 1,000 years of light travel across. The pace of things here is measured, vast and calm. Now consider what Webb found when it pointed its instruments away from the outer arm, inward toward the galactic center. The same galaxy, the same Milky Way we have always inhabited, but a completely different world. At the heart of the Milky Way lies a region astronomers call the Central Molecular Zone, the innermost stretch of the galactic disk, roughly 1,000 light-years across. 1,000 light-years. If the outer arm where we live is the countryside, the Central Molecular Zone is the downtown core. Dense, packed, active on every scale, with a gravitational giant at its very center. To feel the difference in density, take a breath of air right now. The air filling your lungs is roughly 10,000 trillion molecules per cubic meter. The interstellar space in our neighborhood, the space between the stars of the Orion Arm, contains only a few hundred atoms per cubic meter. Almost. Perfectly empty. But move into the Central Molecular Zone and the interstellar medium thickens dramatically. The clouds of gas and dust packed into these inner regions are thousands of times denser than the space around us. Not dense by human standards, still far emptier than any vacuum we could achieve in a laboratory, but dense enough, in cosmic terms, to collapse under gravity and birth stars. Dense enough to hide entire stellar nurseries from every telescope we had built before Webb. At the very center of this zone sits Sagittarius A star, the supermassive black hole anchoring the entire galaxy. A gravitational colossus with a mass 4 million times that of our Sun. To picture that, our Sun is already so massive that its gravity holds 8 planets in orbit across billions of kilometers. Sagittarius A star outmasses our Sun by a factor of 4 million, and circling it, within just a few hundred light years, are some of the most extreme environments in the entire Milky Way. Here is the puzzle that haunted astronomers for decades, and that Webb is now beginning to illuminate directly. Stars form in clouds of gas and dust when those clouds grow dense enough for gravity to overcome the internal pressure holding the material apart. The cloud collapses. The center heats up. A star ignites. The denser the cloud, the more raw material, the more star formation. This is the basic logic of how galaxies work. And by this logic, the Central Molecular Zone, with its extraordinary concentration of gas packed into a relatively small region close to the galactic engine, should be the most productive star-forming region in the entire Milky Way, the factory running at maximum capacity. But the reality is very different. The galactic center region, despite all its raw material, produces stars at a rate far lower than the models predict. The predictions, built from observations of star formation in other parts of the galaxy, including the outer arm, where results are much more predictable, consistently expected more activity than astronomers actually measured. The inner core of the Milky Way looks on paper like the perfect environment for intense stellar birth, and in practice largely, the birth rate is suppressed. No one has fully resolved this paradox. The galactic center should be one of the most productive star-forming regions in the galaxy, and largely, strangely, it is not. But then there is Sagittarius B2. Astronomers had known for decades of this massive molecular cloud. a region of dense gas sitting only a few hundred light-years from Sagittarius A star, close enough to feel the gravitational churning of the central black hole, embedded in the same suppressed extreme environment that restrains star formation across the broader galactic center, studied from the outside in radio waves and millimeter wavelength light, understood to be large and dense but broadly expected to behave like everything else in the inner galaxy. Then, in September 2025, NASA released Webb's first detailed infrared observations of Sagittarius B2, images taken simultaneously with two separate instruments, revealing the region in wavelengths no previous telescope had ever been able to study at this depth. What Webb showed was not what anyone had anticipated. Sagittarius B2 is producing stars at a rate completely inconsistent with its surroundings. Completely. The galactic center region holds the bulk of the available star-forming gas in that part of the galaxy. Sagittarius B2 holds only 10% of it, and yet Sagittarius B2 produces 50% of all the stars being born in the entire galactic center. Half the star formation from a tenth of the material. University of Florida astronomer Adam Ginsberg, who led the Webb program, described the significance plainly. The telescope's images are revealing detail we've never been able to see before, and will help us understand some of the still elusive mysteries of massive star formation and why Sagittarius B2 is so much more active than the rest of the galactic center. The mystery is genuine. No current model fully explains why this single cloud, embedded in a region where star formation is broadly suppressed, is performing at such an extraordinary rate. Webb's images reveal one possible clue. One end of Sagittarius B2 shows a straight, sharp edge, as if something enormous pressed against the cloud from one direction and compressed it, triggering a burst of star formation that the rest of the inner region has somehow avoided. But whether that explanation accounts for the full picture remains, honestly, unknown. And then there is what the images showed about the darkest parts of the cloud. The regions in Webb's images that look like holes, areas where the stars simply seem to vanish, where the picture goes quiet and empty, are not empty at all. They are so dense with gas and dust that even Webb cannot see. Through them, the most powerful infrared telescope ever built, looking in wavelengths that pass through dust clouds that block all visible light, still cannot penetrate these structures. Future stars are forming inside them, wrapped in a darkness so complete that no instrument currently in existence can reach the stars within. Some of what the galaxy is building at its very core remains, for now, beyond our reach. But the deeper revelation from Webb's inner galaxy observations is not the star-forming mystery of Sagittarius B2. The deeper revelation is what is suppressing star formation everywhere else. Magnetic fields. In 2023, Webb captured an extraordinary image of Sagittarius C, a stellar nursery sitting approximately 300 light-years from Sagittarius A star, deep inside the galactic center region. The near-infrared camera image covered a patch of sky just 50 light-years wide. 50 light-years! If our Sun were at one edge of that image, the nearest star to us, Proxima Centauri, 4¼ light-years away, would still be well inside it. That narrow a slice. And inside that 50 light-year window, an estimated 500,000 stars are visible. 500,000 stars in a region of space we could theoretically walk across on foot if we had an unimaginable number of years to spare. The density of the galactic center, made visible for the first time, is almost impossible to reconcile with the quiet of the neighborhood we described. But it is not the stars alone that make the image extraordinary. Running through the image, in the region of hot ionized hydrogen plasma, plasma being gas so energized it has been stripped of its electrons, turned electrically charged, Webb revealed dozens of long, thin filaments, elongated threads of glowing material, stretching in ordered patterns through the star-forming cloud. Not random, not diffuse, structured, as if something invisible was threading the gas into shape. Follow-up research published in the Astrophysical Journal by University of Colorado Boulder, astrophysicist John Bally and colleagues identified what is shaping them. The tidal forces from Sagittarius A star, the gravitational churning created by 4 million solar masses at the center, stretch and amplify the magnetic fields threading through the surrounding gas. Think of it like this. Take a tangled collection of iron filings and run a powerful magnet along one edge. The filings orient. They line up. They take on a structure the magnet imposes without touching a single filing directly. The supermassive black hole, through gravity alone, is doing something similar to the magnetic fields permeating the gas clouds within a few hundred light years of its event horizon. And those amplified magnetic fields are doing something that should, by ordinary galactic logic, be impossible. They are resisting gravity itself. Instead of dense gas clouds collapsing inward to birth stars, which is what dense clouds do in every other well-studied region of the galaxy, the magnetic forces in the galactic center keep the gas threaded, suspended, held in those long filaments rather than falling. Star formation is suppressed not by a lack of material, but by invisible lines of force, amplified by the black hole that simply will not let the material fall. Bally put the question as directly as science allows. If there is so much dense gas and cosmic dust here, and we know that stars form in such clouds, why are so few stars born here? And then the answer Webb is beginning to reveal. Strong magnetic fields may play an important role in suppressing star formation, even at small scales. Not modelled from the outside, not inferred from equations. Directly observed for the first time in the images Webb returned from a region no optical telescope had ever honestly reached. What Webb's observations of Sagittarius B2, Sagittarius C, and the surrounding inner regions have collectively produced is a picture of the Milky Way's hidden architecture that no previous instrument could have assembled. The galaxy's interior is not a denser, simpler version of the outer arm. The forces at work in it, magnetic fields, gravitational tidal forces from the central black hole, radiation from massive young stars blasting the surrounding gas, shockwaves from protostellar jets, turbulence operating at scales from individual star-forming clouds to the sweep of the entire central molecular zone, interact in ways that produce results no straightforward model predicts. A star-forming region outperforming everything around it, while its neighbours are suppressed. Filaments of plasma organised by forces we cannot see. Structures so opaque that even the most advanced infrared telescope in human history cannot see through them. Samuel Crowe of the University of Virginia, who led the original Sagittarius C observations, described it in the simplest and most honest terms. There's never been any infrared data on this region with the level of resolution and sensitivity we get with Webb, so we are seeing lots of features here for the first time. Features. Plural, many of them not yet explained. Features for which the science of galactic structure does not yet have complete answers. This is the hidden architecture, not a static diagram of arms and clouds and a black hole at the center. A dynamic, layered system where gravity, magnetism, radiation and chemistry are in continuous and complex negotiation, and where the outcomes of that negotiation shape whether stars are born or suppressed, whether structures collapse or persist, whether the galaxy we call home grows or stays as it is. And all of it, every cloud, every filament, every star and every arm, is in motion, has always been in motion. The structures Webb has revealed in the inner galaxy are not standing still. Nothing in the Milky Way stands still. The galactic center churns, the spiral, arms rotate, the gas flows, and our own solar system, having spent 4.5 billion years inside this system, has been tracing a path through the Milky Way at a speed no human technology has ever approached. A path that has carried us through different stellar environments, through regions of varying density and radiation, through conditions that have shifted over geological time, in ways that left their mark on the very Earth beneath us. The question of where we are in this galaxy is inseparable from the question of where we have been, and the story of our motion through it, the path our solar system has traced, and what that path has done to the conditions on Earth over hundreds of millions of years is one of the most surprising and consequential discoveries in modern astronomy. Because the galaxy does not just surround us, it has been shaping us all along. Nothing in this galaxy is standing still, not a single star, not a single cloud of gas, not us. Everything is moving, and has been moving for billions of years, tracing paths through the galactic disk that are slowly, quietly reshaping what life on Earth has experienced. The galaxy is not a backdrop, it is a force, and it has been acting on us all along. We tend to think of the night sky as fixed. The stars appear in the same positions they appeared last year, and the year before, and the year before that. The same constellations, the same patterns, the same slow seasonal rotation as the Earth moves around the Sun. On a human timescale, the sky is the closest thing we have to permanence. The stars do not seem to move. Orion rises in winter. The Southern Cross anchors the southern hemisphere sky. The Big Dipper wheels slowly overhead. The map appears unchanged. But this appearance is an illusion produced by the brevity of a human life. Everything in the sky is moving. Every star, tracing its own path through the galaxy. Every cloud of gas drifting on timescales that dwarf human civilization. And our own solar system, carrying the Earth and everything on it, has been hurtling through this galaxy at a speed that should feel impossible, along a path that has taken us through environments radically different from where we are now. A path that has been shaping the conditions of life on this planet for as long as life has existed. And it is only now, with the precision instruments of the modern era, that we are beginning to trace that path with real accuracy. Our solar system orbits the center of the Milky Way at approximately 230 kilometers per second, which translates to roughly 828,000 kilometers per hour, or about 514,000 miles per hour. That number requires a moment, 800,000 kilometers per hour. To put that in terms of something tangible, in the 90 seconds. It might take you to read this passage aloud. Our entire solar system, the Sun, the Earth, the Moon, every planet, every comet, every asteroid, moves approximately 20,000 kilometers, or about 12,500 miles, along its orbit around the galactic center. 12,500 miles in 90 seconds. At that speed, you could cross the continental United States coast to coast in roughly 2 seconds. And yet, in a galaxy 100,000 light-years wide, this extraordinary velocity makes us feel nearly stationary. The distances involved are simply that vast. Even at this speed, one complete orbit around the galactic center, one full loop, back to roughly where we started, takes approximately 230 million years. Astronomers call this a galactic year, or sometimes a cosmic year. The last time we were in this part of the galaxy, the first dinosaurs were just beginning to appear on Earth. The Triassic period was underway. Pangaea was beginning to fracture. Whatever ground you stand on right now was part of a continent that looked nothing like any modern landmass. And the solar system, in all that time since, has completed exactly one loop around the galactic center. One orbit, a single revolution. The galaxy moves in time that makes geological history feel like an afternoon. Since the Sun formed approximately 4.5 billion years ago, our solar system has likely completed somewhere between 18 and 20 full orbits of the Milky Way. 18 to 20 complete laps around the galactic center, across nearly 5 billion years of time, each one a journey through different environments, different stellar densities, different radiation levels, different encounters with the spiral arms and the interstellar medium, each one quietly writing conditions into the story of Earth and into the story of life. Here is where things grow significantly stranger and significantly more important. When we think of things rotating, we tend to picture them spinning as a unified object. A wheel, a coin, a planet, everything connected, everything moving at the same angular rate, the outer edge completing one rotation in the same time as the inner hub. This is how a solid body rotates, and it is emphatically not how the Milky Way rotates. The galaxy rotates differentially. Different parts of it orbit at different speeds, with the inner regions completing their loops around the galactic center faster than the outer regions. Stars in the crowded inner disk move faster around the center than stars in the quieter outer disk. Our own Sun, at 26,000 light-years from the center, orbits at roughly 230 kilometers per second. A star much closer to the core would orbit significantly faster. A star much farther out would orbit more slowly. The whole system is not turning like a rigid plate. It is more like a fluid in motion, with every ring of the disk completing its circuit in a different amount of time. This has a profound consequence for the structure we see. The spiral arms of the Milky Way are not fixed structures. They are not the same material moving together in formation. The stars currently in a spiral arm will, over millions of years, drift out of it, and new stars will drift in. The arms themselves are best understood as regions of enhanced density, like slow-moving waves through the disk, through which stars and gas pass and are temporarily compressed, triggering star formation as they do. Stars enter a spiral arm, new stars ignite within it. Those new stars age and drift out as the density wave moves on, and the arm maintains its shape not through fixed membership, but through continuous replacement. Think of it like a slow-moving traffic jam on a long highway. The individual cars, the stars, move through it at their own pace. Some arrive and some depart. The jam itself appears to hold position, a persistent region of compression, while the cars that make it up are constantly changing. The spiral arm is the jam. The stars are the cars. And our solar system has passed through several of these jams during its history, crossing from one interarm region into the denser compression of a spiral arm and out the other side over timescales of many tens of millions of years. For most of modern astronomy's history, the Milky Way was imagined as essentially flat. A disk, like a vinyl record, like a frisbee, like a coin. Yes, it had a bulge at the center. Yes, the arms curved outward. But the overall disk itself was thought to lie, more or less, on a single plane. The maps drawn of our galaxy depicted it as a relatively tidy, symmetrical structure spreading outward from the center in a single flat layer. Scientists were not wrong to assume this. Every edge-on galaxy they could observe nearby looked flat. The physics of rotating disks suggested flatness. The math supported it. The observation supported it. The assumption had been comfortable, logical, and widely accepted for decades. But the reality is very different. The Milky Way's disk is warped. Not slightly, not technically, dramatically, measurably, and in motion. The outer disk, beyond roughly 30,000 light-years from the center, curls upward on one side and downward on the other, tracing an S-shaped curve across the full extent of the galaxy. The shape is sometimes compared to the brim of a hat, bent at opposite ends, curving up to the north in one direction, down to the south in another. The warp was first detected in the 1950s through radio observations of hydrogen gas in the outer regions, but the full extent of it and what is causing it remained unclear for decades. Then, using precision distance measurements from Gaia combined with studies of variable stars called Cepheids, stars that pulsate in brightness in a regular, reliable way that allows astronomers to calculate their exact distances, like a known brightness lamp placed at a measured distance, astronomers built the first genuinely accurate three-dimensional map of the warped outer disk. And what they found showed the warp to be far more pronounced and far more dynamic than earlier estimates had captured. The warp is not static. Gaia data published in research led by Eloisa Poggio of the Turin Astrophysical Observatory confirmed that the warp itself precesses, meaning it slowly rotates around the galactic center, like the wobble of a spinning top. One full precession takes somewhere between 600 and 700 million years. That wobble is moving faster than any known force, other than a direct gravitational disturbance, could easily explain. And the leading theory, strongly supported by the Gaia data, is that the warp is caused by the ongoing gravitational influence of a smaller galaxy currently in the process of colliding with the Milky Way, sending ripples through the galactic disk. The way a stone dropped in still water sends rings spreading outward from the impact point. Our galaxy is being distorted, slowly, over hundreds of millions of years, being bent by a collision it has not yet finished, and we, sitting in the Orion Arm at 26,000 light-years from the center, are caught up in this distortion, not dramatically, not dangerously, but as passengers in a system that is itself in a process of continuous, dynamic, gravitational negotiation with the universe around it. And there is one more dimension to our motion that most people never consider. Our solar system does not trace a perfectly flat orbit around the galactic center. The plane of our solar system is tilted at approximately 60 degrees relative to the Milky Way's galactic plane. As a result, as we orbit the center, we also bob, oscillating vertically, rising above and descending below the flat midplane of the galactic disk, like a horse on a carousel that not only goes around but also moves up and down. This vertical oscillation follows its own timescale, roughly 60 to 70 million years per complete cycle above and below the midplane. Right now, the Sun sits approximately 50 to 60 light-years above the galactic midplane, slightly north of the flat center of the disk, currently on the upswing of one of these long oscillations. Over the next tens of millions of years, we will continue rising, reach a peak of perhaps a few hundred light-years above the disk, and then sink back down through it and below, completing one cycle before rising again. Why does this matter? Because the density of stars, gas, and cosmic radiation varies significantly with height above the midplane. When the solar system passes through the densest part of the galactic disk, it encounters more interstellar material, more molecular clouds, more gravitational perturbations, potentially more encounters that disturb the distant comets of the outer solar system and send some of them inward toward the inner planets. Some researchers have proposed that this regular vertical cycling may correlate with periodic fluctuations in the rate of cometary impacts on Earth. The evidence for this connection is debated, and the science is genuinely unresolved. But the question itself is remarkable. The rhythm of our vertical motion through the galactic disk may be written, in some way, into the geological and biological record of Earth. Understanding galactic motion requires knowing where everything is, and knowing where everything is requires cutting through the dust. This is precisely where Webb's infrared vision contributes something that no previous mapping effort could provide. The velocity and motion data from Gaia tells us how stars are moving. Webb tells us, in new detail, what those stars are, their ages, their masses, their compositions, information hidden inside the dusty inner regions of the galaxy that older instruments could not reach. Together, the two observatories are assembling a picture of galactic dynamics, motion mapped to structure, velocity mapped to environment, in a way that was genuinely impossible before. Webb's observations of star-forming regions in the inner galaxy, combined with Gaia's stellar motion data for the outer disk, are beginning to reveal the full three-dimensional choreography of the Milky Way, where new stars are being born, how those stars are moving after birth, how the spiral arms are physically structured at their densest inner regions, and how the outer disk's warp and oscillations are influencing the distribution of star formation across the galaxy's full extent. What is emerging is not a static picture, not a diagram in an astronomy textbook, a living, moving, continuously evolving system, galaxies colliding in the outer regions, magnetic fields threading the inner core, star-forming waves oscillating through the arms, and our own solar system tracing a long, slow, bobbing spiral through it all, passing through different environments on timescales that dwarf anything in human experience, but that have nonetheless, quietly and persistently, left their marks on the history of life on this planet. We began this story inside a forest, trying to measure something too large to see from within, and what we have gradually uncovered is not a fixed structure, but a dynamic one, a galaxy in motion, warped by ongoing collisions, threaded by magnetic fields, organized by density waves and gravity into arms that are always changing, and crossed continuously by a solar system that has been tracing its own long path through all of it for nearly 5 billion years. This is not a backdrop. The Milky Way is an actor. But until very recently, all of this understanding came from looking inward, at our own galaxy, from our own position within it. The next question is a different kind of question entirely, because Webb has also been looking outward, and what it found when it pointed its instruments at galaxies beyond our own, galaxies that look, in some cases, startlingly like a younger version of the Milky Way, has forced scientists to reconsider not just where we are, but what kind of galaxy we live in, and whether the Milky Way itself is as ordinary as we have always assumed. We have been studying the Milky Way from the inside, looking outward through layers of dust and stars, measuring what we can reach, inferring what we cannot. But Webb has also been looking in a completely different direction, not inward at our galaxy, but outward across billions of light years. And what it found out there is, in a strange way, a story about home. Science often makes the most progress by accident, not by looking for the expected result, but by finding something no one was searching for, in a place no one was specifically looking, a discovery that arrives sideways, from an observation pointed at something else entirely. These serendipitous finds are sometimes the most important ones because they carry no confirmation bias, no expectation to satisfy. The data simply shows you something, and you either see it or you don't. What Webb showed us in the early universe was something so unexpected that it is still reshaping the models astronomers use to understand how galaxies form. And it is not just that what was found was surprising. What is genuinely strange is what it implies about our own galaxy, and about us. To understand why what Webb found matters, we need to understand what everyone agreed on before it. For decades, the standard picture of galactic evolution was well established and internally consistent. The universe began in the Big Bang approximately 13.8 billion years ago. In the early universe, the first few billion years of cosmic history, conditions were chaotic. Galaxies were small, irregular and turbulent. They were clumping together, merging, colliding, still building up mass. The large, structured, organized galaxies we see in the universe today, the elegant spirals with defined arms, the bars of densely packed stars running through their centers, the stable rotating disks, took a long time to emerge. Specifically, it was believed they took billions of years to grow and stabilize into those characteristic shapes. The Milky Way is a barred spiral galaxy, a galaxy with not just curved arms sweeping outward, but a straight bar of tightly packed stars running through its central region, with the arms branching off the ends of that bar. Think of the letter X at the center, with curved lines sweeping off each tip. This bar structure requires a certain amount of stability to form and maintain. The stars orbiting through it must be moving in orderly, coordinated patterns, not in the chaotic, turbulent flows that dominated the early universe, where galaxies were still violently colliding and assembling themselves from smaller pieces. Bars need calm, and calm, the consensus held, takes time, several billion years minimum. Barred spirals like the Milky Way were, according to the established models, a later development, features that emerged only after the universe had significantly settled and matured. Scientists were confident in this picture. The physics supported it. The observations supported it. The models agreed. They were wrong. Not slightly wrong, dramatically wrong. In November 2023, a team led by researchers at the Centro de Astrobiología in Spain published a study in the journal Nature that described the most distant barred spiral galaxy ever observed. They named it CEERS-2112, and what made it extraordinary was not just its distance, but when it existed. The light Webb captured from CEERS-2112 had been travelling for 11.7 billion years before arriving at the telescope. 11.7 billion years. When that light left its galaxy, the universe was just 2.1 billion years old, roughly 15% of its current age. At the time that light departed, Earth did not exist. Our Sun did not exist. The matter that would one day become our solar system was not yet assembled, and in that early, turbulent cosmos, CEERS-2112 already had a central bar of stars, a mature, organized, structured feature in a barred spiral galaxy remarkably similar in type to our own, at a time when nothing of the sort was supposed to exist. Astronomer Alexander de la Vega of the University of California, Riverside was one of the co-authors of the study. He described his own initial skepticism. He had expected that measuring the properties of such a tiny, distant galaxy would be riddled with measurement uncertainty, but Webb's precision was sufficient to put strong constraints on the bar's size and shape. The bar was real, and its existence, de la Vega said, suggests that galaxies matured and became ordered much faster than anyone had predicted. The models of galaxy formation, he stated directly, need revision. The implications are twofold. The formation timeline for organized galaxies was wrong, not by a small margin, but by several billion years. And something unknown is allowing structures like bars to emerge and stabilize in environments that were supposed to be far too chaotic to support them. That unknown, in many researchers' current thinking, likely involves dark matter, the invisible gravitational scaffolding that pervades the universe and holds galaxies together. Dark matter may have been playing a more central and faster-acting role in organizing early galaxies than the models previously assumed, but the details of how remain an open and actively debated question. And then, in April 2025, the record was shattered again, in a more extreme way than even CEERS-2112 had managed. The galaxy was discovered by accident. Webb has an observing mode called pure parallel, a way of using two of its instruments simultaneously, pointing in slightly different directions, so that while the main instrument studies one target, a second camera is quietly capturing a different patch of sky for free. The panoramic survey, led by Christina Williams of NSF Noir Lab and Pascal Oesch of the University of Geneva, was collecting this bonus data during unrelated observations. No one was specifically searching for what they found. A postdoctoral researcher named Mengyuan Xiao, working through the images at Geneva, saw something in the data that stopped her. A galaxy. Organized. Structured. With a central bulge, a vast rotating disk of star-forming gas, and spiral arms extending outward, unmistakably the architecture of a mature galaxy. Nothing unusual so far, except for one detail. The light from this galaxy had been travelling for approximately 12.5 billion years before reaching Webb. 12.5 billion years. When that light departed, the universe was just 1 billion years old. 1 billion. The universe had barely begun, and this galaxy, which the team named Zhulong, meaning torch dragon, after a mythological creature from Chinese tradition associated with light and the alternation of cosmic time, already looked in its essential form like the Milky Way. Zhulong's disk spans roughly 60,000 light-years. The Milky Way's disk spans approximately 100,000 light-years, so it was somewhat smaller, but that difference is a matter of degree, not kind. The structure was the same: central bulge, rotating disk, spiral arms, and its stellar mass, the total mass of stars it had already assembled, exceeded 100 billion times the mass of our Sun. The Milky Way's stellar mass is estimated at around 46 billion solar masses. Zhulong had assembled more stellar material, in a more organized form, in 1 billion years, than current models comfortably explain. Xiao described the discovery simply: what makes Zhulong stand out is how much it resembles the Milky Way in shape, size, and stellar mass. Williams, co-leading the program, was equally direct. It is generally thought that it takes billions of years for this kind of structure to form. Zhulong shows that it can also happen in 1 billion years. Wesch framed the significance even more broadly. This discovery is fundamentally changing our view of the early universe. The models are not small adjustments away from being right. Something more fundamental is operating in early galaxy formation than the standard picture captured. What exactly that is, how gas cools and collapses fast enough, how dark matter halos organize themselves on these timescales, what triggers the orderly rotation needed for spiral arms to emerge and survive, remains genuinely unresolved. The question is open, and it is, scientists acknowledge, an important one. But here is what these discoveries do beyond challenging formation timelines. They place the Milky Way in a family. Before Webb, the picture of the early universe was one in which organized, stable, spiral galaxies like ours were rare, late-forming exceptions in a cosmos of chaotic early structures. That picture implied something somewhat singular about where we live, a galaxy that required exceptional time to reach its ordered form, perhaps unusual in the broader context of the cosmos. Webb has replaced that picture with a very different one. Galaxies resembling the Milky Way can emerge early. They existed when the universe was a fraction of its current age. They are not late arrivals. They are not exceptional in their structure. The type of galaxy we live in, barred spiral with organized arms, a rotating disk, a central bar, has been forming since at least the first billion years of cosmic time, and while Zhulong and CEERS-2112 are rare at their distances and epochs, their existence implies that the conditions allowing organized spirals to form are not uniquely modern. They were available earlier than anyone expected. What does this mean for our understanding of the Milky Way? The Milky Way is not an aberration, not a special case requiring a special explanation. The structure of our galaxy, the thing we have been trying to map, to measure, to understand from within, is a feature of the universe that appears across cosmic history. When we look at Zhulong, we are, in a real sense, looking at a younger version of the class of galaxy we inhabit. A galaxy that formed the same kind of structure we live within over 12 billion years ago, under conditions our models are still working to fully understand. We are not an island. We are part of a family. And that family, it turns out, has been producing galaxies like ours for nearly the entire history of the universe. And this opens a question that runs deeper than galaxy morphology, deeper than whether early spirals should or shouldn't exist. If galaxies resembling the Milky Way can form and stabilize in the first billion years of cosmic time, then the conditions required for that formation, the specific distribution of dark matter, the rate at which gas cools and collapses, the triggers for organized rotation, were present very early. And if they were present very early, then the question of why the Milky Way looks the way it does, and how it came to host the specific conditions that allowed a star like our Sun to form in a stable, quiet arm of a stable, organized spiral. That question acquires a different context. We formed here. We formed in this galaxy, in this arm, in this particular position within the disk, in a universe where galaxies with exactly this architecture have been emerging since nearly the beginning of cosmic time. That is not a small thing. The structure that houses us is not a late accident. It belongs to a pattern written into the universe from very near its origin. But here is where the story deepens further, and in a way that connects these distant galaxies, back to questions about our own. Because what Webb is revealing about the early universe is not just that organized galaxies existed sooner than expected. It is also raising profound and unresolved questions about what made them that way, about the forces, both visible and invisible, that shaped the cosmos into something capable of producing structures like the one we call home. Looking at Zhulong is, in a way, looking at a kind of cosmic photograph of what the universe was doing long before the Earth existed. A galaxy organized, structured, rotating, the same basic architecture as the Milky Way, assembled in 1/10 the time our models expected. And this raises a question that connects directly to the deepest layer of the story we have been building across all of this. A question about what is actually driving galaxy formation at the most fundamental level. Not just what shapes the spiral arms, or what triggers star formation, or what warps the outer disk, but what provides the invisible scaffolding that holds all of it together. What makes the entire structure possible at all? Something that cannot be seen, cannot be directly detected, and yet accounts for the vast majority of all the matter in the universe. We have been watching galaxies form, watching structures emerge from chaos, and lurking behind every discovery in every chapter of this story is the same invisible presence, the thing that organized these galaxies, that defined their halos, that governs their motion, and that we still cannot directly see or touch. Understanding it is not a detail. It may be the central fact of what the Milky Way is, and of how we came to exist within it. Every galaxy we can see is the end result of a process that began in the first moments after the Big Bang. Not by design, not by intention, but because the early universe contained the right kind of structure, invisible, gravitational, and entirely unlike anything we have ever touched, to make galaxies possible at all. Understanding the Milky Way means understanding that structure, and that structure is mostly something we cannot see. Take everything you can see in the night sky, every star, every smear of the Milky Way arcing overhead, every distant galaxy visible through a telescope. Take all of it, every atom of ordinary matter across the entire observable universe, every planet, every cloud of gas, every black hole, every grain of dust drifting between the stars. Now set all of that aside. The matter you set aside represents only 5% of the total mass energy content of the universe. 5%. Everything we have ever detected, measured, named, touched, built, studied, or mapped, every particle of matter and energy that interacts with light in any way, amounts to 5% of what actually exists. The remaining 95% is something else. Something that does not emit light, does not absorb it, does not scatter or reflect it. Something that passes through ordinary matter as if ordinary matter were barely there. We have never directly detected it. We do not know what it is, and without it, no galaxy in the universe would exist, including ours. The invisible component that makes up the bulk of the universe's mass falls into two broad categories. The first is dark matter, which constitutes roughly 27% of the total mass energy content of everything. The second is dark energy, a still more mysterious force driving the accelerating expansion of the universe, making up the remaining 68%. The ordinary matter we know, the atoms that build stars and planets and people, sits in the remaining 5%. A thin skim of familiarity on an ocean of the unknown. Dark matter is not just a background detail. For galaxies, it is the foundation. In the standard picture of cosmology, the universe began in the Big Bang approximately 13.8 billion years ago, in an almost perfectly uniform state, with everything spread nearly evenly across all of space. Nearly evenly, but not quite. Tiny fluctuations in density existed from the very first moments. Regions that were infinitesimally denser than average. These fluctuations were real. They were imprinted in the cosmic microwave background, the faint glow of light left over from the early universe that satellites like the European Space Agency's Planck mission have mapped in extraordinary detail, and those tiny fluctuations, fractions of a percent denser than the surrounding universe, were enough. Dark matter, moving under gravity alone, began to collapse around those denser regions, not slowly and gently, but over hundreds of millions of years, accumulating into enormous invisible structures, dark matter halos. Halos the size of which dwarfs any galaxy that would eventually form within them. The Milky Way's dark matter halo, by current estimates, extends to roughly 1 million light-years in every direction, 10 times the width of the visible galaxy itself. If you shrank the Milky Way's visible disk to the size of a dinner plate, the dark matter halo surrounding it would span a room. Into these halos, ordinary matter, the gas and hydrogen and helium that came from the Big Bang, fell. Gas follows gravity. It fell inward, it cooled, it condensed, it began to spin as it collapsed, and eventually it reached densities high enough for stars to ignite. The first galaxies were not the organized, elegant spirals we see today. They were small, chaotic, irregular knots of star-forming gas, embedded in the invisible scaffolding of dark matter, halos that were themselves still growing, still merging, still building up their mass. This is the story of how galaxies begin, not from stars, but from invisible gravity. For most of human history, dark matter was invisible in every sense, undetected, unmeasured, and not even suspected. The shift came largely in the 1970s, through the careful work of astronomer Vera Rubin and her colleague Kent Ford. Rubin was measuring the rotational speeds of stars in spiral galaxies at different distances from their centers. The expectation, based on how we understood gravity at the time, was clear. Stars far from a galaxy's center should move more slowly, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. The math was straightforward, the prediction was settled, but it was wrong. The outer stars in galaxy after galaxy moved at roughly the same speed as those closer in, sometimes even faster. The rotation curves, as astronomers call them, graphs of orbital speed versus distance, from a galaxy's center, refused to fall off the way physics said they should. The only explanation that fit was that something vast and invisible, something extending far beyond the visible galaxy, was providing additional gravitational pull, not at the center of the galaxy, everywhere, a massive, diffuse spherical halo of unseen material surrounding the entire disk. Rubin's data pointed to it clearly, and the implication was profound. The part of any spiral galaxy we can see, the part that glows, that forms stars, that makes the pinwheel pattern we associate with the word galaxy, represents only a fraction of what is actually there. For the Milky Way, the numbers are striking. Visible stars, gas, and dust, the material we can directly observe and photograph, account for roughly 20% of the galaxy's total mass. The remaining 80% is dark matter. 4/5 of the Milky Way is invisible. You are a passenger in a structure that is mostly something we have never seen, and now, with more precise data, we are beginning to understand that the dark matter halo surrounding the Milky Way is not just present, it is actively shaping the galaxy we live in. In 2023, a team at the Harvard-Smithsonian Center for Astrophysics, led by astrophysicist J.J. Hahn, published research showing that the Milky Way's dark matter halo is tilted, not perfectly aligned with the flat disk of the visible galaxy, but angled at an oblique inclination, and this tilt, the team found, provides the most complete explanation yet for why the Milky Way's outer disk is warped and flared in the way it is. The invisible halo is bending the galaxy it contains. We cannot see the cause, but we can see the effect, written into the shape of the disk we live within. Here is where the story of the Milky Way's origin becomes genuinely astonishing. For decades, astronomers assumed the Milky Way had grown relatively quietly, gradually assembling mass from the surrounding intergalactic medium, slowly converting gas into stars across billions of years without any particularly dramatic events in its recent history. A stable, middle-aged spiral galaxy building up its mass in a roughly orderly fashion. The textbook picture. But the galaxy's stars tell a different story, and Gaia read it. Within the data from Gaia's stellar survey, buried inside the positions and velocities of nearly 2 billion stars, there was a population of stars moving in patterns inconsistent with ordinary disk dynamics. Stars with unusual orbits, unusual chemical compositions, unusual ages, orbiting the center of the Milky Way on elongated looping paths that cut through the galactic disk at odd angles, like stones skipped across a pond rather than logs floating downstream. Stars that appeared, by their chemical signatures, to have come from somewhere else, a smaller, separate galaxy. In 2018, a team of researchers identified this stellar population and what it meant. The Milky Way, approximately 10 billion years ago, collided with and absorbed a substantial dwarf galaxy, a smaller galaxy containing several hundred million stars, now called Gaia Enceladus, or the Gaia sausage. The collision was not a gentle encounter. The dwarf galaxy fell in, its stars scattered into the halo and disk, and the collision itself played a significant role in sculpting the structure of the Milky Way we live in today. The thick disk, the older, denser layer of stars beneath the thinner star-forming disk, formed partly as a result of the dynamical disruption this collision caused. The Milky Way is not pristine, not untouched, not quietly self-assembled. Our galaxy bears the imprint of a violent merger that happened 10 billion years ago, and the stars from that ancient collision are still orbiting around us today, carrying their foreign chemical signatures like a language we can now read. 10 billion years ago, when that merger happened, the Sun did not yet exist. Our solar system would not form for another 5.5 billion years. The galaxy that would one day contain our star and our planet was still being violently reorganized by a collision with a galaxy it had consumed. The Milky Way does not sit alone. Our galaxy is part of a gravitationally bound collection of galaxies called the Local Group, a cluster of more than 50 galaxies spread across a region of space roughly 10 million light-years across. 10 million light-years. The observable universe spans approximately 93 billion light-years. The Local Group occupies a tiny corner of it. The two dominant members are the Milky Way and the Andromeda Galaxy, two massive spiral galaxies roughly similar in scale, separated by approximately 2.5 million light-years. 2.5 million light-years. Even at the speed of light, the journey from one to the other would take 2.5 million years. And Andromeda is the nearest major galaxy to our own, the closest, the neighbour. The distance that separates us from our nearest galactic neighbour is 2.5 million years of light speed travel. Andromeda is approaching, moving toward us at about 110 kilometers per second, roughly 68 miles per second, fast by any human measure. At that speed, a spacecraft could cross the continental United States in under a minute, and yet the distance between the two galaxies is so vast that this motion requires billions of years to close. Previous estimates, based on Hubble Space Telescope measurements published in 2012, concluded that Andromeda was on a near-certain collision course and would reach us in approximately 4 billion years. But the reality, as is consistently the pattern in this story, turned out to be more complex. In 2025, a team led by astronomer Till Sawala of the University of Helsinki published a new analysis in Nature Astronomy, incorporating the most precise measurements of stellar motions yet available from both Gaia and Hubble, and including the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, two significant additional members of the Local Group that previous calculations had largely ignored. The conclusion: the The probability of a direct collision between the Milky Way and Andromeda within the next 10 billion years is only about 50%. In roughly half the simulations, the two galaxies pass each other at a distance and enter a slow orbital decay rather than a direct crash. The fate of our galaxy, Sawala stated directly, is based on the best available data, uncertain. An almost equal probability for the collision, or for the two galaxies surviving unscathed. This is not a failure of astronomy. This is precisely what science looks like when new data genuinely changes the picture. The old consensus, stated with full confidence in 2012, has been revised by better measurements in 2025. The Milky Way's long-term fate remains an open question. The discoveries Webb has made in the early universe, the organized spiral galaxies forming in the first billion years, the massive structures assembling far faster than the models predicted, carry a direct implication for understanding why the Milky Way looks the way it does. For years, the dominant model of galaxy formation predicted a clear hierarchy. Dark matter halos form first. Gas falls in and cools. Small galaxies form within small halos. Small galaxies merge into larger ones over billions of years. Large organized spirals like the Milky Way emerge late in this process, after sufficient merging and settling has produced the stability needed for extended disks and persistent spiral arms. Webb is showing that parts of this picture were wrong about the timeline. Organized spiral galaxies, massive ones with structures closely resembling the Milky Way, were assembling in the first billion years. The conditions for their formation were available far earlier. This does not mean the broad framework is incorrect. Dark matter, halos still appear to be the gravitational foundation. Ordinary matter still falls in and forms stars. The hierarchy still broadly holds. But the pace at which it operates, the speed at which organized structures can emerge, was underestimated significantly. What this means for the Milky Way is that the galaxy we inhabit belongs to a class of structures that the universe was producing nearly from the beginning, not a late, exceptional product of an unusually stable corner of the cosmos, a natural consequence of the dark matter scaffolding and the physics of cooling gas, one that the universe was generating across cosmic time at rates and timescales that are still being fully mapped. We are, in the most literal sense, the product of processes that began in the very first moments after the universe came into existence. The dark matter fluctuations that seeded our galaxy's halo formed in the first fractions of a second. The ancient merger that reshaped our disk happened 10 billion years ago. The stellar nurseries that gave birth to our sun ignited 4.5 billion years ago. And all of it, the dark matter scaffold, the ancient collision, the formation of our star, the assembly of our planet, connects back to conditions set in place before anything we can touch or see had yet formed. That is not a poetic flourish. That is the timeline, verified by measurement, written in the motions of stars. We have moved from the edge of our galactic neighborhood to the origin of the universe itself, and found that the story of where we are is inseparable from the story of how everything began. The Milky Way did not simply appear, fully formed, in a quiet corner of the cosmos. It was assembled across billions of years from ancient collisions, dark matter gravity, cooling gas, and stellar generations too, numerous to fully count. And yet, for all of this understanding, one thread of the story remains unresolved, the thread that has run through every chapter, from the maps of the inner galaxy to the discovery of Zhulong, from the warp of the outer disk to the uncertain fate of our collision with Andromeda. Dark matter remains undetected at its fundamental level. We know what it does. We can measure its effects with extraordinary precision. But what it actually is, what particle, what property, what aspect of physics gives rise to the invisible scaffolding that shapes every galaxy in the observable universe, remains one of the deepest open questions in all of science. And it is a question that the next generation of instruments, Webb, and those that will follow it, are actively pushing toward answering. Not from inside the forest, but from every direction the telescope can point. Every instrument we build becomes obsolete. Every map we draw gets redrawn. That is not a failure. That is precisely how science is supposed to work. And what makes this moment in astronomy genuinely different from every era before, it is not just what we have found. It is what we are about to find, with tools that have never existed until now, trained on places we have never honestly seen. The James Webb Space Telescope has been in orbit since December 2021. That is approximately 4 years of active science operations. In those 4 years, it has imaged stellar nurseries no optical telescope had ever reached, measured star formation in the galactic center with unprecedented clarity, found spiral galaxies forming in the first billion years of the universe, revealed magnetic filaments threading the inner Milky Way, uncovered ancient merger signatures in the motions of stars that have been orbiting our galaxy for 10 billion years. And yet, by any reasonable measure, Webb is still just beginning. The telescope was designed for a minimum mission of 10 years. Based on the precision of its launch trajectory in 2021, current estimates suggest it has fuel reserves sufficient for considerably longer, potentially 20 years or more. In November 2025, the Space Telescope Science Institute received a record-breaking number of proposals for Webb's 5th annual observing cycle, more than 2,900 submissions from astronomers around the world, 2,900 separate scientific programs competing for time on a single telescope. The astronomical community's appetite for what Webb can reveal shows no sign of slowing. Among those proposals, 32 were joint programs combining Webb's observations with those of another instrument. An instrument that has recently produced some of the most detailed images of the Milky Way's inner regions ever assembled, and together, these two observatories are beginning to construct something no generation of astronomers before ours has had access to: a genuine, three-dimensional, multi-wavelength portrait of the galaxy we live in. Let us be honest about what we know and what we don't. We know the broad shape of the Milky Way, its diameter, its central bar, its major spiral arms, the approximate position of our solar system within it. We know our galaxy has a massive dark matter halo extending far beyond the visible disk. We know the galactic center is dominated by a supermassive black hole surrounded by one of the most extreme environments in the observable universe. We know the outer disk is warped, and we have strong hypotheses about why. We know the Milky Way consumed a smaller galaxy approximately 10 billion years ago, and that the stars from that ancient collision are still orbiting around us today. But the spaces between what we know are wide, genuinely wide. The three-dimensional structure of the Milky Way's spiral arms, not their positions mapped approximately from radio observations, but their precise shapes, their exact star-forming activity, their chemical composition at different points along their length, remains largely unmapped. The outer disk, beyond roughly 50,000 light-years from the galactic center, is so poorly observed that new star-forming structures are still being discovered in it with modern instruments. The flows of gas that feed the central molecular zone, the pathways by which material travels from the outer spiral arms inward to fuel the star formation we can now image near the galactic core, are tracked only in broad outline, not in the detail that would allow us to understand precisely how the inner galaxy's extreme environment is sustained, and the nature of dark matter, the invisible substance that constitutes 80% of the Milky Way's mass, the scaffolding without which the galaxy would not exist, remains the deepest open question in astrophysics. We know what it does. We do not know what it is. In September 2024, Webb turned in a direction that no space-based infrared telescope had ever pointed with this level of precision, toward the very outskirts of our galaxy. The region astronomers call the extreme outer galaxy, a sparse, ancient zone located more than 58,000 light-years from the galactic center. more than twice as far from the galactic center as we are, in a part of the Milky Way so chemically primitive, so poor in the heavy elements that form only in later generations of stars, that it more closely resembles the composition of a dwarf galaxy than the familiar stellar environment of the Orion Arm. A team led by Natsuko Izumi of Gifu University, using telescope time allocated to Mike Ressler of NASA's Jet Propulsion Laboratory, directed Webb's near-infrared camera and its mid-infrared instrument at two molecular clouds in this remote region, called Digel Clouds 1 and 2. The data revealed star formation in unprecedented detail, newly forming stars still wrapped in their birth cocoons, jets of material ejected along the poles of protostars, the first clear imaging of this process in the extreme outer Milky Way. Structures that, before Webb, astronomers knew existed, but could never examine closely enough to describe. And what makes this observationally important extends beyond the beauty of the images. The extreme outer galaxy's chemical composition is nearly identical to what the Milky Way itself would have looked like in its early history. Before multiple generations of stellar birth, nuclear fusion, and supernova explosions had enriched the interstellar gas with heavy elements. Studying star formation in these outer clouds is, in a real sense, studying a living fossil, a region of the galaxy that has not significantly evolved since the earliest epochs of galactic history, still forming stars under conditions that closely mirror the infant Milky Way. And Izumi's team was explicit. This was just the beginning. They intend to return. But here is the wider picture that the extreme outer galaxy observations represent. Our galaxy spans approximately 100,000 light-years from edge to edge. We sit 26,000 light-years from the center. The majority of the detailed observations of the Milky Way structure, from the galactic center imaging of Sagittarius C and Sagittarius B2 inward, have been focused on the inner galaxy. The outer half of the disk remains, in many respects, a frontier, a vast region that even Webb is only beginning to explore. The forest is much larger than our maps have suggested, and we are still in the early chapters of learning its true shape from above. Webb does not work alone, and in understanding the Milky Way's hidden architecture, the combination of instruments now converging on the same targets is beginning to produce something unprecedented. In February 2026, researchers from the European Southern Observatory and an international team published the results of the ACES survey, the ALMA CMZ Exploration Survey, conducted using the Atacama Large Millimeter/Submillimeter Array, a collection of 66 radio telescopes located in the Atacama Desert of northern Chile at an altitude of 5,000 meters or 16,000 feet. The ALMA array detects radiation in the millimeter and submillimeter wavelengths that pass through cold gas and dust that even infrared light cannot fully penetrate. And where Webb reveals the stars and warm dust of the galactic center, ALMA maps the cold molecular gas, the raw material from which those stars were made. The ACES survey produced the largest image ALMA has ever created, a mosaic spanning more than 650 light-years of the central molecular zone, assembled from hundreds of individual observations, like pieces of a cosmic puzzle fitted together one by one. The image is equivalent in the sky to the width of 3 full moons placed side by side, and within it, ALMA identified more than 70 different types of molecules drifting through the galactic center, from simple compounds like silicon monoxide to complex organic chemicals including methanol. 70 distinct molecular species, each one a chemical fingerprint of the environment that produced it, each one a clue about the conditions that shape star formation in the most extreme region of our galaxy. Ashley Barnes of the European Southern Observatory, a member of the ACES team, described the result simply: a place of extremes invisible to our eyes, but now revealed in extraordinary detail. And the team was direct about what comes next. The ALMA wideband sensitivity upgrade, a major improvement to the telescope array's signal collecting power, currently being implemented, will resolve even finer structures. And when the European Southern Observatory's extremely large telescope comes online, its 40-metre or 130-foot primary mirror, the largest optical and near-infrared telescope ever built, will be combined with ALMA and Webb data to push observations of the galactic centre to resolutions and depths that no instrument currently in existence can achieve. Together, these instruments form something genuinely new in the history of astronomy. A multi-layered, multi-wavelength network of observatories, each one seeing a different component of the same structure, each one contributing a layer of information that the others cannot provide. Webb sees the stars and the warm dust. ALMA sees the cold gas. The extremely large telescope will resolve individual stars in previously inaccessible regions. Gaia provided the three-dimensional motion data for more than 1 billion stars. Future data, releases from Gaia's successor missions, will refine those positions further still. The three-dimensional map of the Milky Way that previous generations of astronomers could only dream of, the one that was impossible as long as we could only work with visible light inside a dust-filled disk, is now genuinely being assembled. Not by any single instrument, but by many instruments working together, each one compensating for the limitations of the others, building a picture that none of them could produce alone. But the questions that remain open are not small gaps in an otherwise complete picture. They are central to everything. We do not know the true nature of dark matter. Despite constituting 80% of the Milky Way's mass, despite shaping the galaxy's rotation curve and determining the structure of its halo, despite being required by every successful model of galaxy formation we have ever constructed, no experiment has directly detected a dark matter particle. Not one. The largest underground detectors, the most sensitive experiments, the most carefully designed particle physics searches have all returned the same answer: nothing. Dark matter remains inferred entirely from its gravitational effects. We know it is there because of what the galaxy does. We do not know what it is made of. We do not know how gas actually flows from the outer disk inward to feed the central molecular zone. We can trace broad outlines. We can identify the molecular filaments that carry material toward the center. But the detailed pathways, how gas moves from the spiral arms into the inner galaxy, what sustains the reservoirs of star-forming material near the galactic center against the forces that should disperse them, why the central molecular zone hosts so much gas but converts so little of it into stars, remain genuinely unresolved. We do not know how many ancient stars populate the outermost halo of the Milky Way. The halo, the vast, diffuse spherical shell surrounding the visible disk, containing the oldest stars in the galaxy, many of them relics of the earliest epochs of galactic history, extends perhaps 200,000 light-years in every direction. The stars within it are so distant, so faint, so sparsely distributed that current surveys have captured only a fraction of them. How many there are, what they can tell us about the very first stages of the Milky Way's assembly, what mergers and collisions their chemical signatures record. These are open questions, and answering them requires instruments like Webb, with the sensitivity to detect individual ancient stars at enormous distances, combined with the wide-field surveys that can cover enough sky to find them. These are not the questions of a field approaching completion. They are the questions of a field at the beginning of a new era. There is a question worth sitting with for a moment. Why does any of this matter? Not to professional astronomers, their reasons are evident, but to the person watching from a quiet room at night, to you. The answer is not simply that these are fascinating puzzles. The answer is that what we learn about the Milky Way's structure, its formation, its dynamics, and its future is inseparable from understanding the conditions that allowed our star, our planet, and our existence to emerge. Our position in the Orion Arm, at the particular distance from the galactic center that we occupy, in the particular epoch in the galaxy's history in which we find ourselves, these are not arbitrary details. They are the specific conditions that produce the chemical environment, the radiation levels, the gravitational stability, and the stellar generation timing required for a solar system like ours to form. Understanding the Milky Way is, at its deepest level, understanding why we are here at all. And right now, at this specific moment in the history of human civilization, we have the tools to do that in a way no previous generation could. Webb is operational. ALMA is producing the most detailed maps of the galactic center ever assembled. The extremely large telescope is under construction. The data from Gaia continues to be processed and released. For the first time in history, all of this is happening simultaneously, each instrument contributing a layer that the others cannot provide, all of it converging on the same profound set of questions. We are standing at higher ground than we have ever stood before, and for the first time we can genuinely begin to see the shape of the forest. The map is not finished. It may never be fully finished. Every answer generates new questions, and the Milky Way, dynamic, ancient, warped, full of invisible mass, still consuming smaller galaxies, still forming stars, still being shaped by forces we are only beginning to understand, keeps offering new surprises. But something has changed, something fundamental. The forest that was once impossible to see from within, the galaxy whose shape we could only approximate, whose inner regions were hidden behind walls of dust, whose past was written in stellar motions, too fine to measure, is becoming visible. Not all of it, not yet, but genuinely, measurably scientifically visible in a way that previous generations of astronomers could not access. And that visibility carries a consequence that reaches far beyond the structure of spiral arms or the flows of molecular gas. Because at the end of all of this, after the maps are drawn, after the models are revised, after the questions are replaced by deeper questions, what we are actually doing is understanding our place in the universe in a way that no civilization before ours has ever managed. Standing inside the forest, looking outward through layers of stars we cannot rise above, and building slowly, carefully, with extraordinary tools and extraordinary patience, the higher ground that lets us see. The final question this raises is not a question about the galaxy. It is a question about us, about what it means to be a species that can look at a structure 100,000 light years across, a structure we have always lived inside without ever being able to see, and begin, with quiet persistence and remarkable ingenuity, to understand it. That question, and what it reveals about the relationship between human consciousness and the cosmos it finds itself embedded within, is where this journey must finally land. We started in a forest, deep inside it, unable to see its shape. That is still where we are. We haven't left. But somewhere in the course of this journey, something shifted. Not the forest, not our position within it, something in us, in how we understand what it means to be standing here at all. Consider what you knew at the beginning of this story. You knew the Milky Way was a galaxy. You knew it contained billions of stars. You knew, in the broadest sense, that our solar system was located somewhere within it. Perhaps you had some picture in your mind, a flat spiral, a white band of stars on a clear night, a vague awareness of something vast surrounding us. That knowledge was real, but it was the knowledge of someone standing in the forest, looking at the nearest trees and concluding that the forest was roughly this dense and roughly this tall in every direction. Not wrong exactly, but incomplete in a way that mattered, incomplete in a way that changed the meaning of where we stood. What we have built together across this journey is something different, not a complete picture. We were clear about that. The map is still being drawn. The dark matter is still undetected at the particle level. The gas flows feeding the galactic center are still only broadly traced. The three-dimensional structure of the outer spiral arms is still largely unexplored. The questions that remain are genuinely large ones, not footnotes. But the shape of our ignorance has changed. And that matters. Knowing what you don't know, knowing precisely where the edges of the map are, and why those edges exist is a fundamentally different relationship with the unknown than simply not knowing that any edges exist at all. We followed a thread from the surface of a problem down through layers of extraordinary complexity. We began with the fundamental challenge that we are inside the galaxy, surrounded by it, unable to step outside and see it whole. That the same dust clouds that birth new stars also block the view of every optical telescope ever built. That 4 centuries of careful astronomy had produced a map that looked complete but was silently, significantly incomplete. A map that stopped at the edge of visibility and presented that edge as the edge of knowledge. We followed that problem to its partial resolution, to the infrared instruments of the James Webb Space Telescope, which passed through interstellar dust the way a radio signal passes through walls that would stop sound, revealing stellar nurseries and star-forming regions that had been entirely hidden. We watched those instruments illuminate the galactic center for the first time, the magnetic filaments threading the plasma near Sagittarius A star, the paradoxical productivity of Sagittarius B2, the dark patches so dense with forming stars that not even Webb can see through them. We moved outward from the center to our own neighborhood, a cavity blown open by ancient supernovae, surrounded by a wave of stellar nurseries that undulates through the Orion arm like a slow galactic tide. We learned that our arm of the galaxy was more significant than its old classification as a minor spur suggested, that a structure we thought we understood was quietly larger and more active than our previous measurements had captured. We felt the motion, the solar system's long, slow, vertical bobbing through the disk, its orbit around the galactic center at speeds that should feel impossible, the differential rotation that winds the spiral arms into their characteristic shapes. We understood the warp that bends the outer disk, probably caused by a galaxy currently in the process of colliding with our own, a disturbance that will play out over hundreds of millions of years, utterly indifferent to the scale of anything human. We looked outward to find ourselves reflected in distant galaxies, Milky Way analogues forming in the first billion years of the universe, showing us that the structure we inhabit is not a late accident, but a natural consequence of processes written into the cosmos nearly from its beginning. We trace those processes back to the invisible scaffolding of dark matter, the foundation of everything visible, the material that constitutes 4/5 of the galaxy's total mass and remains, at its fundamental particle level, completely unknown. And we arrived at the frontier, the combination of instruments now converging on the same questions, building a 3-dimensional portrait of our galaxy that no single generation before ours could have attempted. A portrait that is incomplete, that will remain incomplete for years, but that is, for the first time, genuinely beginning to take shape. Pause here for a moment. Set aside the science, the measurements, the discoveries. You have travelled, in the space of this single documentary, from the surface of the problem to the depths of the origin story of the universe itself. From the forest floor to something approaching height. That is not nothing. That distance travelled in one sitting at night is a genuinely remarkable thing to have done. This is the part of the journey that no instrument can make for us. Not Webb, not Alma, not Gaia. The part where the knowledge becomes personal, where the vast impersonal distances and timescales settle into something felt rather than merely understood, where 26,000 light-years stops being a number and becomes a quiet recognition of the gulf between where we are and the center of the thing we live within. We share this forest. Every human being who has ever lived has spent their entire existence inside this galaxy, at this address, in this particular arm, in this particular bubble of ancient supernova remnants. Different cultures, different centuries, different languages, all of them looking up at the same band of pale light across the same dark sky without knowing what they were seeing, without yet having the tools to ask, We have those tools now. We are living right now inside the most productive era of Milky Way science in the entire history of human curiosity about the sky. We began this story in a forest, standing deep inside it, surrounded by trees in every direction, trying to measure something too large to see from within. The shape of the whole, its true extent, its real structure, what it looks like from above, permanently out of reach. Every map we drew, stopping at the edge of visibility and presenting that edge as if it were the edge of the world. That is still where we stand. We have not left the forest. We are still, physically, embedded inside a galaxy we cannot rise above, surrounded on all sides by its stars and dust and gas. That is a fact that no telescope changes. No instrument has moved us. We are still here at 26,000 light years from the center, in a quiet bubble on the inner edge of a minor arm, looking outward through layers of material we can only partly penetrate. But something has changed, and the change is not where we stand. The change is that we have learned to read the forest, not from above, not yet, perhaps never fully, but from within, through the language of infrared light, of molecular chemistry, of stellar motions tracked with extraordinary precision across billions of individual stars. We have learned to hear the magnetic fields in the plasma near the galactic core, to read the chemical signatures of ancient stars that once belonged to a different galaxy, to recognize the shape of a structure in 3 dimensions from the careful assembly of its parts, the way a blind person learns a room not by seeing it from outside, but by moving through it with extraordinary attention. The forest has not become smaller. If anything, it has grown. We have learned how much deeper it runs than we knew, how much richer its interior, how much older its history. The map has grown more detailed in the places we can reach and more explicitly blank in the places we cannot. Blank in a way that is no longer disguised as completion, but openly marked as the edge of current knowledge, the frontier where the next generation of instruments will begin. That is not the same as still being lost. That is something new, something that did not exist before the era we are living in. A genuine understanding of our position that is partial, honest about its partiality, and more richly informed than any previous human generation has possessed. The Milky Way is not a fixed object. It was never a fixed object. Every image ever drawn of it as a flat pinwheel with neat spiral arms was always an approximation, a snapshot of a dynamic, churning, continuously evolving system, frozen in a single moment of its billion-year life for human eyes that could not perceive the motion. Our galaxy has consumed smaller galaxies. It is consuming small ones still. The Sagittarius dwarf galaxy is currently being torn, apart and absorbed into the Milky Way's disk, its stars scattered into streams that arc across the galactic halo like the slow-motion ghost of a collision that began hundreds of millions of years ago. The outer disk bends and wobbles under the gravitational influence of a neighboring galaxy still approaching. The central bar rotates. The spiral arms, not fixed structures, but density waves passing through rotating material, carry new stars through their regions of compression and release older ones into the interarm spaces as they drift through. New stars are forming right now, at this moment, in the Orion Arms stellar nurseries, in Sagittarius B2 near the galactic center, in the remote extreme outer galaxy, in the dense shell of the local bubble's edge. Gas is collapsing, temperatures are rising, fusion is igniting. Stars that do not yet exist will exist within the next 1,000,000 years. Some of them will form planetary systems. Some of those systems will have the right conditions for chemistry to begin, and old stars are dying. Stellar nurseries that burned brightly in the past are dark now, their fuel spent. White dwarfs cool slowly toward invisibility. Neutron stars spin in isolation. Ancient globular clusters, some of them nearly as old as the galaxy itself, orbit in the halo on paths that have barely changed in 12 billion years, their stars slowly cooling, their youngest members billions of years old. All of this is happening simultaneously at scales and on timescales that no human life can witness in its full motion. The Milky Way is alive in a way that no single observation can capture, a living, dynamic entity, as indifferent to our presence as a forest is to the brief lives of the insects that shelter within it. And yet here we are, aware of it, measuring it, understanding, in the deepest sense that word allows, at least something of what it is. There is one question that runs underneath everything in this documentary. Underneath? The dust and the infrared light and the magnetic filaments and the dark matter halos. A question that cannot be answered by any telescope. What does it mean to know where you are, not in the navigational sense, not as a matter of coordinates, but in the deeper sense, the sense in which knowing your place in the universe changes your understanding of what you are and what your existence means? We are not at the center of the galaxy. We are in one of its quieter suburban arms, in a specific bubble carved by ancient explosions on a planet orbiting a middle-aged star that has completed roughly 18 to 20 loops around the galactic center since it formed. Nothing about our position is privileged. The galaxy does not know we are here. The spiral arms do not curve around us. The dark matter halo does not protect us. We exist in the galaxy the way a single note exists in an orchestral score. Real, specific, part of the whole, but not the reason for any of it. And yet, we are the part of the galaxy that can look at itself and understand what it is looking at. We are the matter that became aware of the matter surrounding it. We are the forest, noticing itself. That is an astonishing thing. Not as a comfort, not as a claim of cosmic importance, but as a plain fact about what consciousness is and what it is capable of. The same atoms that formed in the hearts of dead stars, that drifted through interstellar space for billions of years, that eventually assembled into the biochemistry of a living brain. Those atoms can now, through the remarkable accident of being organized the way they are, look outward and recognize the galaxy that made them. We do not know what dark matter is. We do not know whether there are other minds elsewhere in this galaxy, looking at the same band of light and asking the same questions. We do not know the full shape of the forest. We may never know it completely. But we are here asking. We are here measuring. We are here drawing the map with every instrument we can build, correcting it with every new observation, holding it honestly and openly and saying, this is what we know, and this is what we do not yet know, and the distance between those two things is the most alive frontier in human inquiry. The Milky Way has been here for approximately 13 billion years. For the vast majority of that time, nothing within it was aware of it. Then, for a brief, remarkable, geologically instantaneous moment, the blink of a cosmic eye, one small planet in a quiet outer arm produced beings who looked up, recognized the structure around them, and began, carefully, patiently, with extraordinary tools and genuine wonder, to understand it. We are that moment, and it is enough, more than enough.